Good morning, and today we switch over from fundamentals that was covered previously to an application perspective of convective heat and mass transfer. And what we are intending to discuss today is about thermal design of electronic equipment. The emphasis will be laid primarily on electronic equipment, but the discussion can be held, or the topic of interest can be extended to other applications where many of these concepts are applicable. So we move forward, and one of the primary reasons for covering electronics is that electronics cooling is a major driver, or the IT industry is a major growth industry where we all switch over from ordinary analog based systems to an electronic systems, and digital information age is really driving and thriving in our lives. And to give you a perspective, there are about as per some survey and report from Gartner Inc., there's about 12 billion devices connected to internet by 2014, that is 1.7 devices per person. And by 2020, it is expected that there will be about 33 billion devices. That means every person will carry 4 devices per person. That is 4 devices per person. That you can verify yourself how many laptops, tablets, cell phones, computers that you own on your, or say at least you'll have a cell phone that happens to be a smartphone, and then there is a desktop computer or laptop computer at work. So if you start to count them, there are many number of them these days, and that makes it a prolific penetration of these electronics into our day-to-day life. And it is important to understand their behavior, their thermal perspective, and that's what we will discuss today. And our interest and our innate interest in increasing the speed and the amount of information that we want at a very fast rate drives these electronics towards much denser, and the packing of these electronics become much denser. So we will work, or we look into some of these devices and how they grow as we talk further in this. So the first module will primarily discuss the underlying concepts that we need to know before we jump into the actual thermal part of it. So if you look at the revenue that is generated, it is close to $3.8 trillion in 2014, and this is growing at a much rapid rate. So that is one of the primary motivation for understanding or studying this this system, which is the electronic system. So if you look at thermal management of electronics, temperature effects are felt all the way from transistors to the packaged computing devices, which we call sometimes a laptop, a workstation, in some occasions even data centers. Data centers are a group of workstation, if you will, or they are sort of group of servers that are packaged into larger racks, and then n number of racks are deployed in a large room. It's a warehouse type computer. So there is always a need for high performance cooling technologies, because the typical electronics industry is very evolutionary. That is, the industry doesn't change very rapidly, because the emphasis has always been paid into getting faster devices into market as quickly as feasible, because of the competitive nature of the business. So typically disruptive cooling technologies never enter the market that easily unless it is showcased and characterized and all the reliability checks are done a priori. So for example, these days, in 80s and 90s, the electronics grew by what is called Moore's law, that we'll cover in the next slide or two, is that by shrinking the size of the transistors and packing more and more transistors within the same footprint, that gave better performance. Performance, we mean higher speed, and but lately the emphasis has been laid on energy efficiency of these systems. The primary reason is, if you look at a laptop that someone owned in 2000, it consumed about, a desktop would consume about 100 watts. And if there are billion people in this planet and they all own a desktop, then you are talking a big number in terms of electricity consumption, which is 1 billion times 100 watts, which gets close to our gigawatt scale of electricity production just for running these systems. So that was the turning point right around 2004, where people started to freeze the power consumed by these devices and laid emphasis more and more on energy efficiency of these systems. So in terms of thermal management, what thermal management means we'll cover in the next slide or so. But in terms of thermal management, which entails devices like fans, heat sinks, thermal interface materials, all those things, the revenue generated about 2016 is about $10.9 billion, and it is growing at a rate of 6% annually, and it is expected that it will continue to grow at a much aggressive phase with the digital growth that is typically happening in the system, in our lives. So if you look at, give you a simple perspective, a transistor is on the order of 10 power minus 9 or so. The dimension of a transistor is on the order of a nanometer or less than a nanometer, and current day transistor technologies that are shipping in the market is about, the minimum feature size is on the order of 10 nanometers or 7 nanometers, and these transistors are integrated into what is called a silicon die, and that die size is typically on the order of a centimeter or so. Then these silicon dies are packaged. Because these silicon dies themselves do not have power supply, the power supply comes from our wall. In India we have 220 volts, but these transistors need 1 volt or so DC current. Instead we have 220 volts, so we need to find a way to connect these silicon dies to external world. That is the package, that is the role of a package, which is typically on the order of, again, centimeters. And they, depending on the product segment, they can, for example, if you have a smartphone, the power consumed will be on the order of 2 watts, and if it is a desktop workstation, then it could be hundreds of watts. And then because they consume so much power, they also dissipate heat. So in order to dissipate heat, you typically mount a fan and a heat sink these days. In olden days or in smartphones, we don't have fans. Smartphones typically rely on natural convection and radiation, and so the heat sink is on the order of, typically on the order of hundreds of 100 centimeter or 100 millimeter, which is 10 centimeters. And then the heat sinks themselves get packaged into a larger system like a workstation or laptop. Then if they are packaged in a servers, then they go to a facility, and we typically refer to them as data centers, and the facility carries lots of these racks, and the racks themselves are arranged in a row, in number of rows, and that makes up a large data center. So at the data center level, typically the power consumption is close to tens of megawatts, and so that makes it a very interesting problem in achieving these things. From thermal perspective, is that at the transistor level, power density or the heat flux level is important, but at the data center level, the power dissipated is more important. So if you look at transistor, the Moore's law, the so-called Moore's law, which was started in which was something Moore forecasted in 1965, saying that Moore was the founder, director of Intel Corporation. He said that if we can shrink the transistors every 2 years and double the size of a wafer, then you will have quadruple improvement in production, and that indeed shows up as increased revenues. And if you see, based on 2016 data, we are close to having about 10 to 20 billion transistors in such a small area, which is about 1 centimeter by 1 centimeter. So this makes the reason for this enormous growth is revenue generation as well as improvement in energy efficiency and so on. There are so many factors that play in. That's why it is dubbed as Moore's law, even though it is not a law, it is just an observation, and that is how the growth of this sector goes. So that's the brief introduction to what we will be talking about, and the objectives of this presentation would be to introduce concepts with relevance to convective heat and heat transfer in thermal control and management of electronics. What we mean by thermal control is that we emphasize the temperature of the device does not exceed a certain critical limit, and thermal management means if it does exceed, how do we manage that? And those are the two aspects, and we'll discuss very briefly here, and then we provide some appreciation for the applications of first principles that of convective heat transfer to electronics, cooling and packaging problems in industry. So you would have seen lectures covering fundamentals of convective heat and heat transfer, and now we'll take the fundamentals and convert them into applications. So what is electronics cooling? So the electronics cooling here by definition has an objective to maintain the silicon die or device temperature at or below a fixed value to guarantee. A fixed value here means some maximum temperature that you cannot exceed to guarantee performance of the device and reliability while dissipating power to a local ambient. In many occasions the local ambient happens to be air, in some occasions it happens to be water. So the goals of electronics cooling or thermal management is that to prevent catastrophic failures. If the temperature exceeds a certain limit, then the device actually fails. There is what is called leakage currents in these current day electronics. These leakage currents are nothing but they have a very strong dependence on temperature. They have an exponential dependence on temperature. What happens is that as we increase the power, as the temperature rises, the power increases, the leakage loss increases. As the leakage loss increases, temperature increases again. So if you don't provide sufficient thermal control and management, then that turns out to be a positive runaway loop, and so you can even burn your laptop or laptop processor. So in order to provide a reliable operation, we need to ensure that the temperatures does not exceed a certain level. So the other factors that typically are involved are cooling optimization and life cycle costs. The picture on the right hand side shows how a thermal management is done typically in these devices. As the component temperature rises, if it is below a certain limit, then what is called, we define as reliability limit. What we mean by that is that the reliability is secured. Now we are allowed to play with the fan speed or so to optimize cooling or to reduce the energy cost. And let's say for example the damage limit is about 100 degrees C, and these processors these days have thermal sensors in them that continuously monitor temperature of the devices. So those temperature sensors, if it, let's say for example, is set at 100 degrees C, if the temperature sensor reads 100 degrees C, automatically the system or the microprocessor shutdowns by itself. You may notice some of these behaviors in your laptop as the number of years of after n number of years of usage that the laptop shutdowns automatically without you, but you may feel putting your hand at the vent, you will find that very hot air is exiting the system, and so that is the shutdown, automatic shutdown that happens, that is triggered by a software intervention. That is that the sensor on the device reads 100 degrees C, and that say 100 is only an example, it varies from device to device, but 100 degrees C, once it hits, then the software intervenes and says that, oh, I've exceeded 100 degrees C, so I'm going to shut down now to protect my system. So that's how the data is saved by not allowing the device to be damaged completely. The next is, but often people employ what is called a threshold temperature, which is close to a 90 degree, for example, in this case, that if it goes to close to that 90 degree C, then there is always throttling, and you would see that the processors start to run slowly once it reaches 90 degrees C to ensure that the power is not exceeding a certain limit and the temperature is not exceeding. So the power goes down when you lower the speed of the processor, the power consumed goes down, and that makes it easy to optimize the performance, and that makes easy to keep the processor safe and run for longer duration. So a failure of a processor increases or a silicon die increases with temperature. So that's why one has to keep it below a certain level, and so that's what the whole goal of thermal management here is to not only provide heat sinks and thermal interface materials, but also to use software to stop or shut down the system as and when needed. With that definition, we move to an example on the right hand side that shows a processor that had a thermal runaway situation when there was no sufficient cooling was provided. You can see that the device actually burnt out. So there is a big hole in the socket itself during what is called burn-in. Burn-in is a testing phase of a processor, and when it is not, the thermal runaway situation that I had discussed in the previous slide is the reason for the complete burnout of the processor. So in terms of power dissipation, typically if you open a data sheet that is provided by any of the major vendors in the world, which is like AMD or Intel or other companies, they always in their data sheet they provide what is called TDP. TDP is a total design power, or sometimes referred as thermal design power. That is the heat sink and many other thermal management devices are designed based on that power. But there is also something called TDC, that is the total design current. The TDC gives the maximum power that happens to be at the beginning when you start a computer, that there is an inrush of current, and that TDC has to be managed as well if there are larger transients, but typically that is ignored. But one often defines or designs these systems for thermal design power and the ambient temperatures. Because these computers are designed at one location, so they cannot possibly design these cooling heat sinks only for that temperature. So they have to account for the worldwide variation in temperature. So the ambient temperature variation typically is assumed to be on the order of 40 degrees C or 38 to 40 degrees C, and for servers, because they are often kept in a well controlled room environment, the ambient is about 35 degrees. And the co-processors, or recently there is a lot of enormous growth in what is called add-in cards or video cards and other co-processors, like accelerator GPU cards. They often see very high temperatures because they are kept. These cards are often placed at the rear end of a server, and they see a temperature of 45 degrees C. So this ambient temperature is very important in thermal design, because this is the temperature difference that's driving the heat transfer. The processor is at a much higher temperature than this, and the incoming coolant temperature will be on the order of this temperature that we just discussed. And also, if you are designing for a mobile product, one has to account for altitude, and altitude means because the phones need to work even when you are flying in an airplane, or laptop needs to work in a plane, so one has to account for density change as well. So getting to a much deeper picture of this is that if you look at a microprocessor, what is shown as number 1 is in the slide on the left top corner is that you have a heat sink, and there is number 3, which is called the integrated heat spreader, which is often copper, and number 5 is the so-called silicon die that we saw in earlier slide. So that die and the integrated heat spreader is abridged by what is called a thermal interface material. A thermal interface material, when you put two materials together, because of microscopic valleys and peaks, so there's the actual contact area is much reduced compared to what is visually seen, because these microscopic peaks and valleys are the ones that are actually making contact. So one has to, because these devices have very large fluxes, one cannot dissipate that large heat flux by not providing sufficient abridgment between these two materials. For example, in the top left corner, you see that number 4 is called a TIM. TIM is thermal interface material. So there is a TIM between the microprocessor and the integrated heat spreader, and there is another TIM between the integrated heat spreader and the heatsink themselves. So this is the primary thermal architecture. But then if you look at from the die, silicon die and bottom, you see that there is a solder ball, and that is the way the electrical communication happens to the board or this processor. So one often takes a desktop computer and the power is power comes from a wall, but that power is at 220 volt AC, and that current voltage needs to be first converted to a direct current DC, and then the processors and memory devices will have different voltage requirements. The transistors themselves will need about 1 volt or so. So the voltage goes through a number of step down process. When you're stepping down the voltage, then the current that actually runs through these systems actually goes very high. At the die level, one could even see up to 200 to 400 amps of current, DC current, that is running through these processors. So that's, these solder balls provide electrical communication, or power is being delivered through these solder balls to these processors. And what you see as number 7 is what is called the package substrate, often referred to as motherboard. This is a substrate, and that package substrate is often connected to a motherboard through those solder balls. So this is how we see. If you look at the zoom up on the die itself, which is shown as on-chip interconnect, because there are 20 billion transistors and you are trying to arrange them, all these transistors are not isolated. They all need to be connected together. So if you see on the screen that there is an on-chip interconnect, that is a way to connect all these transistors seamlessly into one large unit. So those layers can go up to 9 to 10 or even much higher. The number of layers of these on-chip interconnect could be much higher. So that is the architecture at one go. Because we are passing current through all these on-chip interconnects, there is power generation and temperature heat generation, and so the temperature is also affecting those on-chip interconnect. And what is often referred to as off-chip interconnects are the ones like solder balls. And so we go to the next slide, and this is what a typical package means. Package represents a way of connecting the microprocessors to the motherboard, that is to enable the silicon level interconnects to be connected to the motherboard. And often packages are done to ensure it enables or improves or optimizes the microprocessor performance. The initial role of a package was to provide a mechanical enclosure to protect from external environment, but the role of packaging has improved so much so that nowadays the packaging is the critical element in the whole system. So that is what the packaging goal is. And if you look at levels of packaging, one looks at chip, is often connected to what is called interconnections, and then that is often referred to as the first level, where the chip is connected to a substrate or chip carrier. Those substrates are integrated to a PCB or the motherboard, that is often the second level of packaging, and then the motherboard is integrated into a system level, and that is the so-called third or system level packaging. There are many different ways to look at levels of packaging, but this is the most simplest level of looking at it. One is at first level, second level, and the system level. So finally, to close out the module, we see that there are active and passive sides in a thermal packaging environment, where active side is the die. There is the side we call a heat generation side, and where we mount a heat sink, thermal interface material, spreaders, and so on. And so if you were to draw a resistance network, we'll discuss about resistance network in the next module, is that you often refer to the die as a junction temperature, and then it is connected to a heat spreader, and the heat spreader is connected to an ambient through a thermal interface material and a heat sinks. So that is the goal of this thermal packaging, and that's what we'll spend time on in the next lecture or the next module, which is to follow.